Okay, so for this screencast, we're going to be talking, as you can see here, about the formulas for making simple ionic compounds. And this is going to require us to think about the octet rule once again. And just as a reminder, the octet rule states that atoms tend to lose, gain, or share electrons in order to acquire a full set of valence electrons. And in this case, the full set of valence electrons would be 8 electrons. Okay, so be thinking about octet, 8 electrons. The other thing I want you to recall is that there's a set of metals that have a tendency to form cations. And in fact, there are different types of cations. We can have +1 cations, +2 ones, and we even have some +3 cations that exist. All of the metals that are the alkali metals, the ones in group 1, they all form +1s. And all those in the alkaline earth metals, they form +2s. Metals there. And then if we go over to our group 3, which begins with boron, so I guess I'll just call this the group 3. Some people do call it the boron group, but group 3. Those group 3 form +3 ions. Okay. There are also some transition metals that we're going to be interested in that will form some ions, but it's harder to predict the cations for those. So I'm just going to ignore it for now, and we'll come back to that a little bit later. And then we have some common ions, and the ones that we're really going to focus in on are those that we find in group 6 and in group 7. So group 6 ions are going to form anions that are a -2 charge, and that includes the oxygen group. And like I said, that's going to be our group 6A. And then we have the halides, which is the group 7A, which starts with fluorine, that form -1 anions. Put a little S there. Now, that's going to be really important for us as we begin to start putting these things together and understanding what's happening. Now, don't forget, the octet rule means that we want to make sure that the two atoms satisfy having 8 electrons in their valence shell. So, when you're putting together cations and anions, you always want to start off with the metal first. So, let's go all the way to the simplest ones here, and we'll start with lithium. Lithium forms a +1 ion, and then we'll go all the way to the other side of the periodic table, and we'll take fluorine, and fluorine creates a -1 ion. Okay, in order for lithium to be happy, it likes to lose an electron and therefore have a helium noble gas core, which is nice and stable. And in order for fluorine to be stable and happy, it wants to gain an electron and become a neon core. And again, when you think about the noble gas cores, those things are very stable. So in fact, the fluorine is much more stable as an ion than it would be as a neutral atom. But when we take a look at these things, we can clearly see that lithium and fluorine could really work together as a partnership here, because if lithium wants to take an electron, wants to give away an electron, and fluorine wants to take on an extra electron, well, these two things are going to have a natural affinity for one another. In fact, they are going to bond to one another. So this will cruise over to here, and they will connect. What is important here to understand, however, is that these two fellas right here, when they come together, they always want to form a neutral compound in the end. So it will be Neutral meaning it'll be no charge. So in fact, that will be the case, right? When you put together a lithium with a fluorine, you no longer have the charges associated with it. It's LiF, or lithium fluoride. Now notice how I actually, the name I had for that. You always say the name of the metal, in this case lithium, but for the anion, instead of saying fluorine, I changed the INE at the end of fluorine and I put on a suffix IDE. So instead of calling it lithium fluorine, I actually call it lithium fluoride. It's as simple as that. So the anion, you knock off the end of it, put on IDE instead of whatever it was there, and the metal, the lithium, stays the same. All right, so that's if you have two that are, one is a +1, one is a -1. What happens if we have something like beryllium, which is part of our alkaline earth metals, and Be wants to form a 2+, okay, it would rather form 2+, it would be happier and form an octet there, and then something like sulfur forms a 2-. Same deal here. This is a great partnership because beryllium wants to lose a couple of electrons, sulfur wants to gain a couple of electrons, and so this beryllium will go and snuggle up next to our sulfur. It would then become neutral and become a neutral compound BeS, just like that. Okay? So I want you to think about this. If I had calcium, oops, that's not a good calcium. It's a U. If I had a calcium, which is a 2+, and I wanted it to combine with something in a nice even fashion, well, then I want to check out something that might be a 2-. I could take sulfur again, but perhaps I'll take oxygen, which normally would form a 2- charge. And then I'd go ahead and put that together as calcium with an oxygen. And how would I say that? The name would be calcium. And then don't forget what I need to do here. It wouldn't be calcium oxygen, it would be calcium oxide. This one up here would be beryllium, 2 L's? I think so. Oh boy, I don't remember. But it would be beryllium sulfide. It is important to notice here that sulfur is spelled with an F because a lot of people, I don't know why, but a lot of people think that sulfur's with a PH. Please make sure that you notice that it is with an F there. Okay, so that's it. That's pretty easy to do. This is how you make the names and formulas for some simple ionic compounds. They're called binary compounds because we're talking about two different atoms. But there you have it. Yeah, right. I'll stop right there.